definitions and that. Now, as we said, functions aren't new idea to you or anything. You're familiar with the idea of functions. You're using them all the time in all the maths you do. But in some of this, we're one of the next main topics in this unit to come are the calculus topics. So looking at differentiation and integration. And of course, there you're studying functions are the primary objects of study, functions defined on the real numbers. So it's just in preparation for that, we just want to set up some agreed notation and terminology and so on, and a few little things about functions. But also, there's another small topic in my half of this unit, which is on an introduction to group theory. And being able to talk carefully and precisely about functions is very important for talking about certain types of group as well. Because certain types of group, the objects you're studying, the basic objects you're studying are functions. Not numbers or points in space, but functions between these things. So in a lot of parts of mathematics, functions or mappings between different sets are the primary object of study. So you know, it's important to have agreed terminology and be able to talk precisely about these. Okay. So we introduced terms like domain and codomain. Domain was the set X, which was providing the arguments to the function, the kind of input values to the function, and the codomain Y was the set where the function was taking all its values. And then we had we also looked at the concepts of injectivity and surjectivity, one-to-one and onto functions. And we looked at an example, but just a quick recap on those two before we go on to the following material. So you got this is the notation to kind of declare that f is a function from a set x to a set y. X is the domain, and y is the codomain. So, you know, and this defines values. I mean, we know what a function is, but this defines values f of y, which are elements of the codomain, sorry, f of x, which is an element of the codomain y for each x in the domain large X. Okay, so you've got these values, f of x for each argument, you could say, argument little x in the domain. There's two pictures or visual ways to think about a function. The first is kind of, well, I guess it's not really a Venn diagram, but let's just call it a Venn diagram for this sake. So this is where you kind of draw two blobs to represent the domain and the codomain, and you think of the function f as being some process which is going between these two sets, and you can start sticking down dots here to show the arguments, and start sticking down loads of dots here to represent the elements of the codomain. And you know, you can talk about the behavior of the function by talking about these mapping lines which send an element x here to its value f of x over here. Okay, that's just a kind of visual metaphor for the function. This is very suitable for talking about the properties of injectivity and surjectivity, one-to-one and onto. So the function is not injective when we have situations like, so in this picture you can spot or you can represent non-injectivity because you have two elements of x going to the same element of y. Okay. If the function is injective, you only ever have, like it's shown here, to any particular value in the codomain, you've got at most one arrow coming into it. But if you've ever got two or more arrows coming into the same picture, then that's not injective. That's one example of ways in which you can use this metaphor or visual metaphor for thinking about functions. Also, you could say f is surjective, means every element in y, every element in the codomain has a mapping arrow coming to it. E.g., so you could quickly draw, this would be an example of a surjective function. Just if everything in the codomain is the image or the value of some argument x. Now, to be a well-defined function, we have to define values for every element here, so I could just map these ones onto those same elements. So this function is surjective, or it's suggested a surjective function because every element here in the codomain we see has an arrow coming to it. Of course, it's not injective because there are examples of elements over here with two mapping arrows coming to them. And indeed, this one as well, because there's another mapping arrow here that's joined into it. Okay. So this one is surjective and not injective again. This example. So that way of, it's just a way of representing a function and just kind of illustrating certain things about functions. So in particular, injectivity and surjectivity. So that was the first kind of picture. A second kind of picture is, so that's the first kind of way of representing functions. Another way which can often be useful is a function as a process box. So, or a machine. You think of the function as like something with some kind of machine, and into the machine you feed arguments x, and out of the machine pops values f of x. Okay. So there's some kind of funny process or calculation going on inside the box, and the function is the box, and you stick arguments into the function, you get corresponding values out. Okay. Now this is useful. This is a useful way to think. Useful way to think for, we're going to look at soon compositions of functions, compositions and inverses and so on. Okay, so those are just two kind of mental pictures to have available and which you may find useful. So we looked at injectivity and surjectivity last time. We looked at a couple of examples. We looked at these examples where you had the same underlying process of the sine of an angle, but depending on how you set up the domain and codomain, it would be it could be variously injective or non-injective, or surjective or non-surjective. Okay. Okay. Now, a lot of the time, and indeed most of the time in the rest of this unit, certainly in the calculus, when we're looking at differentiation and integration, we'll be looking at real-valued functions. Okay, so these are functions for which the domain and the codomain are the real numbers, or maybe some restricted subset of the real numbers. Okay, so these are real-valued functions. Now, when you're studying real-valued functions, there are a number of operations you can do on the functions themselves, and these are ultimately come from the type of arithmetic operations you can do on the real numbers themselves. Okay, but we've got these operations of addition, scalar multiplication, multiplication itself, and a division type process or a reciprocal type process, which you can do. Okay, so these are 1, 2, 3, 4 operations that we can do on functions. So if you're given a pair of functions, these first 3 operations, 3, 7, 3, 8, and 3, 9, these show you how to construct a third function, a new function out of the 2 basic functions. Okay, so you can add 2 functions together. So if you've got 2 real-valued functions f and g, you can add them together, gives you a new function, and its values, I mean, to say what the new function is, you have to be able to say what all its values are, because it's the values that define a function. So the value of the function f plus g on an argument x is simply the value it has on f and the value it has on g. You add the 2 together. Okay. So the addition you do between functions is defined as the addition you do between their values. You can multiply a function by a scalar. So a scalar is just some other number, lambda, real number lambda. And so you can form a new function lambda times f. This is a new function, and its values are lambda, the real number lambda, multiplied by the corresponding value of the original function f. Okay? So the function lambda f, evaluated at an argument x, is lambda times the value f of x. You can do the same thing for multiplication. Have 2 functions, you can multiply them. Gives you a new function, which is defined as the product function f times g, evaluated on an argument x. It's the product of the 2 values f of x and g of x. And you can do a very similar thing with the reciprocal operation, dividing 1 by the object. So you can form a new function 1 over f, and it has the property that the value 1 over f takes on x is defined as 1 over f of x. Now, of course, you do have to avoid 0. For that type of situation, you have to be dealing with a function which avoids 0. So you'd want to be dealing with a function that never takes the value 0. Either because the underlying process of the function never does take the value 0, or that the function f is working on a restricted domain, so that any zeros of the underlying process aren't elements of the domain. So the function itself never takes the value 0. Okay. Now there is this convention, of course, that sometimes you can write the reciprocal of a number as, 3 to the power 1, 2 to the power 1. These mean, we have this convention that means 1 over 3, 1 over 2, etc. But we don't use that. This convention is not used for functions. Okay, so if f is a function, I'm just writing here what's in the notes. If f is a function, f inverse means the inverse. Sorry, f to the power 1 means the inverse function. The inverse function, not the reciprocal. One over f. So don't get confused with that. So we'll be defining soon the idea of an inverse function. Okay, and that's what f to the power minus 1 is used for. Of course, in some special cases, the inverse function is that right? Maybe. I won't finish that thought. Okay. So those are kind of arithmetic operations you can do with functions, with real valued functions. And those generalize to functions defined on more general systems than the real numbers. So what have I called them? These arithmetic operations will generalize. If you're if you are studying functions f between some more general set, so not the real numbers necessarily, then if arithmetic type operations exist on the codomain Y, so if the set of values of the function, the codomain of the function, the set where all the values of the function live, if there are arithmetic type operations going on here, so if there's like addition-like operations or multiplication-like operations going on here, then the functions kind of inherit those. Just using these same definition formulae here. Okay, because all the operations on the right-hand side of those definitions, the addition, the scalar multiplication, the multiplying f of x by g of x, those are operations that are all taking place in the codomain of the function, if you think about it. Okay, because the objects that you're operating with there are elements of the codomain. And of course, you're already familiar with situations like this. For instance, vectors. You can have sets of vectors. Okay, well, vectors aren't numbers, but there are arithmetic type operations between vectors. You can add vectors together, at least. Matrices as well. You can have sets of matrices. You can have a function going between sets of matrices, or from some kind of domain, and with the codomain being a set of matrices. Well, you can add matrices together. So it may well be that the operation of matrix addition that's taking place in the codomain will produce an addition type operation on functions defined on matrices, functions from sets of matrices to sets of matrices. Okay. So finish that sentence. If arithmetic type operations exist on the codomain Y, then the set of such functions f from x to y will inherit these operations. Okay. So structure that exists on the codomain can be passed upwards to the set of functions that are landing into that codomain. Okay. So you'll see that when you look at more abstract type of mathematics, you'll see that a lot. Okay. So in this specific example here, we're talking about we've got a set, we're talking about a collection of functions going to the real numbers. So the codomain is the real numbers R, and there are these operations of addition and multiplication on the real numbers, and so the set of real valued functions inherits those operations, or associated operations on the functions themselves. So, okay, any queries about that, or questions about that? Okay. Now, one other type of operation you can do with functions. This is extremely important and very kind of general and deep. It isn't an aspect of numbers. It's much more basic and important than that, or much more fundamental than that. Sometimes you think of numbers as being the most basic building blocks of mathematics, but of course, numbers are already perhaps even some fancy kind of objects. Numbers and their properties. Maybe even there's a much more basic level of mathematics which will study just objects, just the concept of having objects or elements of sets and functions between them, mappings between them, associations between elements. And before you even start to talk about notions of quantity or number or size or magnitude, you can study, study the idea of mappings between objects, and there's a lot of structure there to study. And a very important operation between functions or between mappings that exists is this idea of composition. Now, it's not it's something that in one ways is extremely familiar to everybody, even everybody out on the street. even all the non-mathematicians out there in the world. So this corresponds to the very basic everyday idea, and it's not any kind of mysterious idea. It's very basic, it's very fundamental, of doing one thing after another. Okay, but it's doing stuff. So that's the idea of some kind of process or function, performing some action. And you've got, okay, one thing after another. So this idea of having at least two actions, and you perform one of them first, and then you perform the second action. Okay. So that's, okay, so, you know, that notion exists even before you start looking at it mathematically. Okay. So, but what does it look like when you look at it mathematically? Well, when you look at it mathematically, it's normally phrased something like this in definition 3.11. So here you've got two functions. So these are our two processes, or our things that you can do. So we've got functions f and g. Now you'll notice they're not just any old two functions. There is a relationship between them. The codomain of f is the same as the domain of g. So the place that the set where all the values of f live is the same set where all the arguments of g live. Okay? So f ends, the set where f ends, the codomain of f, is the same as the set where g begins. Okay? So that means you can do f first and then do g on the result of f. Okay? If f is some kind of process which produces an answer or a result in y, and g is a second process which takes things in y and sends them on to another set z. Okay? So you can run the function g after the function f. Okay, but the precise mathematical term we use, the technical mathematical term we use, is composition. So we can compose these two functions to form a new function. And the symbol that's used for composition is this circle. So it's a little circle. So g, and it's read as g after f, or g composed with f. And it's a new function. It will go from the codomain of f to, from the domain x of f to the codomain z of g. And how is it defined? Well, to define a function, you have to say what its values are. Okay? Functions are processes which take inputs and give you values. So you have to be able to say what the values of this composition function are. And g after f, evaluated at an element x from the domain, capital X, is given by this value here, g of f of x. G of f of x. You've got f going x to y, g going y to z, and then you've got the composition function g after f, and that's a function going from x to z, and it's defined by, this is just repeating what's in the notes, but I'm going to show you something. So it's defined by g after f of x is g of f of x. So it's clear that when you're looking at that symbol there for the new function, f is the function that's applied first, and g is the one that's applied second. So it's kind of read from the right, if you like. The opposite way in which we write English. English, we start at the left and you proceed rightwards. Well, when you're reading a composition thing, well, you do read it from the left in the sense you say g after f. But in terms of when the operations are applied, f is the one that's applied first, and then g is applied to the result of it. As you can see here, f is applied to the argument x first, and then g is applied to the result. So in the two pictures that I described before, this can help you think about composition and understand what composition is. Well, in the Venn diagram picture, so you have these blobs for these sets. Well, we should think of three blobs here, an x, y, and a z blob. F is the function going between f and y. G is the function going between y and z. And you can, stick a few arrows in to illustrate what's going on. So there'll be arrows all over this picture, but, I'll just draw in one just to illustrate what's going on. So there's a little element x here. This element here would be the element f of x. And then this element here would be g of f of x. And this overall process then, this process is the process g after f. Okay, so you first perform the operation f, and then you perform g on the result. Okay, and there'll be a whole other maze of arrows going across the diagram, but I'll just draw one, just one chain of arrows going across there. Okay. So that kind of shows you, gives you a visual way to think about the operation of composition. The second way, thinking of your kind of machine boxes for functions, well, that's kind of also one, it gives a neat picture here. Now, if you think about the stuff coming in on the left and the output goes out in the right, kind of like some kind of factory, what do they call it, assembly line or something. So an argument x comes in here, it pops out here in the middle as the value f of x, and that itself is fed straight into the machine of g, and then the final value that pops out is g of f of x. Okay, so you've got your two functions and you're combining them together, or composing them together, and the overall box, so you think of a more complicated machine made up of these two submachines, the overall box is the box labeled g after f. So that's a function that takes inputs x and produces outputs which are g after f applied to an element x, and they're defined like this. Okay. So these are the two ways to visually imagine what composition is. Okay, and it can help you straighten it out. Okay. Now, even before should we look at a couple of examples? Yeah, let's just look at a couple of, because this illustrates this nicely. So if we look at example 3.3, so we're going to take two real valued functions, f and g. So f is the function x squared minus 3, so you can see there, g is the function 2x plus 3. So f is a order 2 or a quadratic type function, quadratic polynomial. G is just a linear polynomial, order 1 polynomial. And we can compose them to produce new functions. Well, we can compose them in two different ways. You can do f after g or g after f, okay? Because in both cases, these are functions going from the real numbers to the real numbers. So the domains and codomains are all the same set, the set of real numbers. So you can compose them in either order. Now, what does the polynomial f after g look like? Well, according to the definition, it should be f applied to g of x. Now, g of x is 2x plus 3. So what we do is we feed 2x plus 3 in as the input to the function f. Now, the function f is the rule that says take the input, square it, and subtract 3. So that's what you do. 2x plus 3, g of x, that's the input to f here. So we need to square it and subtract 3. That's going to give us, you do the algebra, 4x squared plus 12x plus 6, I think. Yeah, 9 minus 6. So the composition f after g is this function, 4x squared plus 12x plus 6. Now, you can compose them in the other way as well. You can do g after f of x. So that's g applied to f of x. Now, f of x, remember, is x squared minus 3. So in the second composition, x squared minus 3 goes in as the input to the function g. And g says, what do you do to the input of g? You double it and add 3. So we need to double x squared minus 3 and add 3. That's going to give you 2x squared minus 3. There's a key observation here, which is this, is that those two compositions are not the same. They're both quadratics. They're both kind of second order polynomial functions, but they're different functions. Okay? And this is a very important property but it's not a specifically mathematical property. It can be seen as an important property of just this very basic kind of pre-mathematical idea of doing one thing after another. Doing one thing after another, it's only in special circumstances that doing it in the two orders leads to the same result. You think about baking a cake. Baking a cake, say, there's two operations in baking a cake. You pour all the ingredients together, you mix them, and then you stick the mixture into the oven. So you got the mixing the ingredients and cooking it in the oven. In some sense, that's what you do when you make a cake. That produces a cake. But if you do those two operations in the opposite order, you take all your separate ingredients, stick them in the oven first, you'll have a load of melted butter, you'll have a load of burnt flour, you'll have a load of poached eggs or baked eggs. So you cook the ingredients first, and then you mix them all together in the bowl. You certainly don't get a cake, you just get some kind of ugly mess, okay? So doing the two operations, it's the same operations you're doing, but you're doing them in the opposite order. It leads to very different results. So it's a fundamental aspect of performing actions after another action. Sometimes they do lead to the same result, but that's kind of special behavior. In general, they don't. And that's what we're seeing here in this example, where has it gone? Example 3.3 there. Two ways of composing those two polynomials leads to different results. Okay, well, we can dive in and try and do a few of these examples. I mean, I can leave some of these for you to explore in the tutorials as well, but we'll just take a couple of them. Maybe G after G after G. Yeah, so let's look at question 5, say. So here we've got a real valued function G. You can think of G as the real numbers to the real numbers. G of x is 2x minus 7. So what is G after G after G going to be? Well, it's going to be a function going from the real numbers to the real numbers. And by definition, G after G after G at an argument x is going to be the rule G of x. 1, 2, 3. Okay, that's the definition of the composition. So here we're composing it with itself twice, if you like. Well, this is going to have some value as a formula. The inner G of x is 2x minus 7. But then you have to apply G to it. Now, what's the rule for applying G? You double the input and you subtract 7. So you'll have to double that and subtract 7. That's performing this middle G, but then you have to perform the outer G. So again, you have to double the input of the outer G. So that's doubling all of that and subtracting 7. So whatever that is, that's the value. So it's 2 times, what's that, 4x minus 7? Minus 7. So it'll be 8x, no, sorry. So it'll be minus 21, minus 14, minus 7. And then you're going to have an 8x, so that'll be minus 42, minus another 7 be minus 49. So it'll be that, won't it? 8x minus 49. So if you have nice enough formulas for real valued functions, you should be able to write down nice enough formulas for any kind of compositions that you can do with them. Now, associated to the idea of composition, we have two very important types of functions, and those are the identity function and inverse functions. Are any questions, first of all, just on composition itself? So it doesn't just hold for real valued functions. It holds for any kind of functions where the codomain of the first one agrees with the domain of the second one. Then you can run the second one after the first one. So in particular, when you've got a set, of functions from some set to itself, so you've got the same set as the domain and the codomain, then you can do any kind of compositions between functions of those types. Okay, because if the domain and codomain is always just the same set, you can combine those kinds of functions together in any kind of way. And that's a very common thing to look at in kind of pure mathematics. So in general, and the kind of general phrase or term for such things is an automorphism. An automorphism is a function, so an automorphism on X, on some kind of set or structure X, is a function f going from X to X. And composition is an important operation on the set of automorphisms of X. So this is one common type of object that mathematicians study in pure mathematics, in algebra. Anytime you've got some kind of an interesting set X, so say the real numbers here for us looking at this example, or it could be some other type, it could be complex numbers, or it could be some set of matrices, or some set of some other kind of objects that you haven't heard of yet, that I haven't heard of. Whenever you've got any kind of interesting mathematical set X with interesting structure or interesting elements, you can study the automorphisms on that set. So all the functions from that set to itself. And the behavior of the automorphisms reveals something reveals facts about the set. Okay? And so very often the object of study is the set of automorphisms under the operation of composition. So even before you talk about any kind of number-like operations on the set X, any kind of arithmetic type operations on the set X, just with the idea of a set, you've already got another set, the set of automorphisms, and an operation on it, the operation of composition. So in some senses, this kind of algebraic situation, a set of automorphisms and the operation of composition, that even exists, or that's kind of more basic than any kind of number type operations or structure that there is in that. Okay. So just before we finish, just a couple of definitions. And again, I think some of the stuff will be familiar to you in some ways. There's the idea of the identity function. So in any set X, there's a special function which you can call id or id, the identity function. And this is the very special function that just takes the value it takes on X is just X. So it leaves every argument alone. It leaves everything unchanged. That's the identity function. Okay, so the output is equal to the input. Okay, that's the identity function. Now, the identity function, with respect to composition, the identity function has this special property that if you compose it with any other function f, it leaves the other function f unchanged as well. Okay, because the input to the function id is always the same as the output. So any of these compositions, f after id, f after the identity, or the identity after f, that's always just going to be the function f. More interestingly, then, we have the idea of a inverse function. And this is when you've got a function f going from x to y, from a domain x to a codomain y, the inverse function is a function going in the opposite direction. So in the Venn diagram picture, we have f going across here. F inverse will be the function going in the opposite direction. Now, inverse functions don't always exist. They only exist in special circumstances. That's when, seeing the definition here, when the function is bijective, and it's injective and surjective. So if each element in the codomain y only has one arrow coming into it, that's being injective. And secondly, every element in the codomain has some arrow coming into it. Then the picture for F inverse is simply just reversing all the arrows. So if I draw F inverse in red, the function F inverse is just the function you get by reversing the direction on all the arrows. It just sends everything back to where it was. And then you get this relationship that F after F inverse, or F inverse after F, is always the identity. Is always the identity function on the appropriate domain. But you can see here that if the function fails to be injective, so if it's not injective, you've got this kind of picture. So you've got two different elements being sent to the same element. Well, you can't reverse these arrows. Well, you can just stick a reverse direction on them, but then you're kind of trying to define an inverse function that, given an input, has two outputs. Well, that's not a function in the sense that we've defined it. Functions just take an input and give you a unique output answer. Okay? So you can't reverse these arrows or these mapping arrows to give you a function. And equally well, if the function fails to be surjective, if there's an element here which doesn't have an arrow coming into it, well, then you obviously can't reverse the direction because there isn't an arrow there to reverse the direction on. In the second kind of picture, in the machine box type picture, so you think of the function f as this kind of thing. It's kind of a simple idea. The function f inverse is just simply the same box, but with the assembly line running in the other direction, if you like. It's the same process, but you're undoing the process. You're feeding in the outputs of the original process, you're undoing the operation, and you're spitting out what were the original inputs, if you like. But of course, you can only do that if every possible element from the set over here is an output of something under f, so you can undo it to produce the original input. And secondly, it can't be non-injective, okay? Because this undoing process has to give you a unique answer for any particular input. Okay, I better end it there, but you can read through. There's a couple of examples there about finding formulae for inverse functions, and that leads you on to some of the tutorial exercises then. Okay, so you can investigate this notion of composition and inverses in the tutorials, and we'll discuss it more next week.